Swayam Prabha. Digital India. Educated India.
Okay, we'll start with the second lab now. So you can all open this Geometric Deep Learning GNN Convolution and Attention PyTorch notebook. So this is basically implementation of GCN layer and graph attention layers here. So everything is implemented. There is no to do in this. Just you can run and experiment with it as you like. So these are the required modules. So we require, currently we are not using geometric in this particular lab. This is just purely PyTorch based implementation. So here you get brief information about how graphs can be fed to PyTorch. So basically there are two ways, as we mentioned in the earlier presentation today in the morning. We can add adjacency metrics as an input, or you can add a list of edges as an input. PyTorch basically most of the time uses a list of edges as the input. So here there is a brief description about the adjacency matrix, and you can just refer to documentation if required. So this is the paper for the graph convolution. You can open it and read it at your time and just see how the simplification they have done. And this is the message passing done for the graph convolution layer. So as you can see, this is the orange one. So orange one's direct neighbor is the green one. So when you pass the layer, so the one orange one would get some properties of the green one. Similarly, if you consider this fourth one, it has got two neighbors, green and yellow. So it has got some properties of both green and yellow. Same thing with the third one. It has also got green and blue. And so this has got the similar vector embeddings basically. And the two has got three neighbors. So it has got the aggregation of this, all these features of these three nodes. So this is the main graph convolution implementation that we will do. In the next lab that is there, we will actually implement this form using the degree matrix and the adjacency matrix one. And we'll also use the PyTorch geometric based pre-implemented layer. We have the dimension as the input and output. And in the forward propagation stage, so basically this is the stuff that is implemented for getting the uh, convolution layer output. So here we are using adjacency metrics and getting the number of neighbors. So this would be used to basically normalize the input that was mentioned in the presentation. Uh, this self-dot propagation is just a linear propagation layers where the features, so for the first layer, it would be just the features. From the second layers, it would be the aggregation of the different aggregation of different features from the neighboring nodes, basically. And we just do the matrix multiplication of the adjacency matrix and the node feature vector. And we just give this normalization. We do normalization of the feature and we return this. So this is all you need to do to implement a GCN layer. So I'll just run this. So now what we'll do is we'll just try running this layer. So for this, we'll have some node features. So from range of 0 to 8 in the form of 1, 4, and 2 tensor. So as you can see, this is just a one in one dimension. These are the four values. So this is the adjacency matrix. So if you consider this graph, then between 1 and 2, there is an edge. So it would be 1. As already I described this in the presentation. So similarly, based on some example, this is the graph we have. And it has got self loop as well. So how did I find out that it has got a self loop? Can anyone just let me know? Do anyone remember how can we identify if it has got a self loop?
because of diagonal
Self,
entries.
correct, correct. So the diagonal entries here are one, so they have got a self connection with them. So this is just an example. Uh, so these are the nodes and these are the adjacency metrics, node features and adjacency metrics. And then we'll create our GCN layer, which has two input and two outputs. So currently we don't want to train this model. So what we will do is we'll initialize the weights and the bias of the projection layer as the identity metrics, nothing else. We don't want to train it. We just want to show an example here. And even we don't want to calculate the gradient, so you can just ignore it. So when you process this node feature and adjacency metrics that we have created, you get this as the convolved uh, feature, you can say, or you can say this is the embedded thing. So one thing to note here is the node features of this two are same. So also in the image also you can see this have got the same color nodes feature. Once they get aggregated, they might end up canceling each other. So for that, this is basically a limitation you can say, or uh, so that is why we also pass this to a non-linear activation function so that we avoid this. So what would be the general structure similar to the convolution layer? Uh, this is the hidden layer, or you can say GCN layer, where we also apply the ReLU activation. You can use sigmoid 10H, anyone you can require. Again, we'll go to second layer, and with that, we'll get an output. You can add a third layer as well. It is up to you. You can stack number of layers. But what was observed in graph neural networks is we do not require too many layers to be stacked upon. Uh, General problems are just solved using two or three graph layers, or you can say two or three message passing layers, and we are able to get good results. If you pass, or you can, if, what I say is, if you have a lot many, or you can say very deep graph layers, you will try to over smoothen the graph, or you can say overfit the data, and that is similar thing as the overfitting of happens in the convolution layers. So basically this can be you can get a good output in just two or three layers. That is what a research has been published. So I haven't mentioned that here, but there is one paper based on that, mentioning about that. So this was just about GCN. For the graph attention thing, so basically it's just a softmax function, and this is the attention value that we need to calculate. The A is the attention, or you can say the weight matrix of the linear projection layer for this particular architecture. And its dimension is 2 cross D messages, because in this, what happens is we try to aggregate feature of every node based on some weights, or you can say some attention values that are there. So the ones which are having higher attention coefficients will get more weight, and you can say those target node. So this is just a way to calculate the attention coefficients, and this is the simplification that is not required basically. So there is another you can say implementation of the same graph attention network where there are multiple heads. For example, for three heads, you have got three attention layers basically, and all that are then averaged or aggregated to a single output. So here we get attention values of all these, and based on all the features from different nodes, we can aggregate this as an output. So here graph attention layer has been implemented. And if you read the paper, it would be more clear compared to what it is mentioned here. So the main idea is just that whichever has got larger attention coefficient, those features would be more prominent in the target node. So this is just the implementation, and this is just the same weight value that are mentioned in the paper that are used here. So it's a lot code, but you can, whenever you get time, you can just refer and understand using reading the paper side by side if required. And same thing we'll do as for graph convolution layer. We'll create a layer. Currently, we just want to understand this, so we don't want to train this model or layer. So we have just initialized the weight as the identity matrix. Bias is at 0, and we use some data, temporary data, to just understand the output. So here you get different values based on the attentions available. So you can try this with multiple values later on when you get time. And so currently, any question related to this lab? I'll give you 5 minutes to just run this lab on your side, and then we'll go to the last lab where we'll compare the performance of our own implementation with the pre-implemented convolution layer. If you have any query, then do let me know.
Hello.
Yes,
In the attention layer, like till number of features.
your voice is breaking. What's your name? Okay. Hello.
Gaurav, we cannot hear you. There's some network issue at your end.
Maybe you can write or post your question on chat then.
Can you explain more attention part? It will just take a limited number of features.
Your voice is breaking, Gaurav. Okay, so for the attention thing, so uh, here for example, for a node, Okay, for this particular node for graph attention. So we want to know which node significantly affects the target node. So for that, we calculate the attention coefficient, the alpha ij that is there. So for that, what we do is we basically calculate alpha ij for all the edges that are there in the graph, and we basically concatenate or you can say aggregate those particular features based on the alpha coefficient. So for so maybe this is having the highest coefficient of 0.5 maybe, and this two might be around one is 0.2, one is 0.5, and another is 0.5. So all this sums up to be 1. So what will happen is we will take multiply that attention coefficient with this feature vector, aggregate here, and all these attention coefficient with other feature vectors will aggregate at the same time here. So what happens is in the single layer, we are able to aggregate the features from different nodes that are available based on the attention coefficient, or you can say whichever has got a higher weight will have significant feature on the output node actually, or you can say the target node. So it is just a general thing that uh, if you are doing some weighted thing, whoever's weight is higher will get higher priority, or you can say those features would be more prominent in the output. And that are basically calculated for all the edges. So the adjacency matrix comes into picture at that point of time. So if you see here, so for all those nodes, basically, we find this A bar, or you can say based on the, so the A bar is the weight of the linear projection layer, linear layer that are there. So for all those weights, we basically calculate alpha ij, and this is basically just a softmax function. So what we'll do, it will just give out the most probable those who is having highest probability as the output, and that value is then multiplied with the uh, weight vector of the node j. So if h1 and h2 is there, so we have calculated alpha ij. So now we'll multiply this alpha 1 2 with this particular weight matrix of the linear projection uh, with the feature vector of this j. So jth is currently the second node. So based on that, we sum for all the neighbors. So now if this has got 2 neighbors or 3 neighbors, for all the 3 neighbors, we calculate it, we get the alpha ij, we multiply it with the weight matrix to get the relevant features in the output node. So we average out, you can say, aggregate those features from all this based on the weights of alpha. Am I clear, Gaurav? You are still not audible. Maybe you can just write down in chat, so that would be good enough. Okay, maybe we can move on to the last exercise quickly. Okay, so for this, we'll be actually using the torch geometric, or you can say PyTorch geometric library. So I have already given the setup path for that, but So whenever you are installing it on your machine, do verify the CUDA version and the PyTorch version that is there. So with this, there is a help for setting up this in your Python environment. So this is basically developed, you can say, after Michael Bronstein just summarized all the graph or the geometric deep learning on non-Euclidean data into his paper. And all the review that he has done in the paper, all the layers or architectures are being implemented in this PyTorch geometric library. So it has also got all the data set that are being used. For example, Cora data set, Mutang data set. So those are okay. For 3D shapes, there is ModelNet is available, ShapeNet is available. So those all data sets would be available with this PyTorch dataset function. And again, so as I mentioned, all the convolution, like for example, if I consider a PointNet paper, or you can say PointNet architecture. So for PointNet architecture, also there is a point convolution layer implemented in Torch geometry. So you can use that to work with the point data for deep learning, basically. So this is how this library came into picture. And there is also transform method that is there. So for example, if you have got an input mesh, but you want to work on point, so you can transform the mesh to a point data before proceeding to the geometric operations. So similar thing, so all this is implemented. You can just refer to its documentation. It's well documented. And this can be used for various applications. So flying convolution and all the layers that are there up till now has been implemented. And you can just try it out whenever you have time on different sub data sets.